Hello everyone. Today we are going to be presenting on containment and ground modification, which is a remediation method. My name is Hattie Davis, and these are my other group members, David, Luke, and Maddie. This is just an overview of everything that we'll be talking about today. We're going to start with the physical mechanisms, different physical characteristics that impact the use of containment and ground modification and how it works all together. Then field implementation, that's just going through different techniques and the equipment that we use for containment and ground modification. Then we're going to get into some influencing factors, different things that make this method work or not work in different circumstances. And then demonstration level, which will just be some case studies and different examples of the use of containment and ground modification. Then we're going to go into applicability and limitations. Again, kind of has to do with influencing factors, things that affect whether it will be successful or not as a remediation method. And then we'll go into some costs and availability. So starting off with physical mechanisms, the first one is impermeability. Impermeability is vital to containment because it's essential for preventing the spread of contaminants through both soil and groundwater, in addition to minimizing the exposure of these contaminants to humans. This doesn't always mean the impermeability of these barriers that we can see in this photo. In this diagram, you see the containment zone, or where the contaminants are, and then surrounding it are all of these barriers that are meant to keep those contaminants in there. Those barriers obviously have to be impermeable to keep those contaminants in there, but in different circumstances, it could also mean just analyzing the surrounding soil material and seeing whether that is permeable or impermeable and whether or not a barrier is necessary, or if the soil itself can contain it already and you'll just need a cap or something like that on top of it, which we'll talk about later. But in a lot of circumstances, these barriers are going to need to be impermeable in order to keep those contaminants out of the aquifer that you can see on the bottom here, or different groundwater or soil, things like that. The next physical mechanism we're going to talk about has to do with particle size and pore space. Particle size can affect the movement of contaminants both inside and outside of the containment area. As you can see in this diagram, with different particle sizes, we'll have different pore spaces. So with larger particles like gravel, you're going to have big pore spaces, definitely in comparison to clay, where you're going to have really small pore spaces that can hold those contaminants in and keep them from moving around and spreading to contaminate different areas or different groundwater or water sources. As I said, fine particles contain contaminants more effectively than larger particles, so something that we'll also talk about later on is a form of ground modification where soil is compressed to decrease that pore space. So even if you have silt, if you apply pressure on top of it, it's going to decrease that pore space and keep those contaminants stuck in there, keep them from migrating. Another method is adding material like cement or clay to fill that pore space. So even if you have something like gravel, if you add smaller particles or even something like cement, it will be able to fill that pore space and contain those contaminants more efficiently. Next, we have structural integrity, which is pretty obvious for containment. The different structures that we use to keep those contaminants in there are going to need to be reliable over time. This is something that can be a downside of containment, because over time you're going to need to constantly monitor it and making sure that it's not breaking down, because we're not removing those contaminants like we are with other remediation methods. Those contaminants are staying in there and we have to make sure they don't spread. So structural integrity is huge for containment. It includes integrity testing of a leak detection network, and then you're going to need a backup leachate collection and treatment system, and the possibility that something does start leaking. And like I said, constant monitoring is important as well. Next, we have volatility of the contaminants. The volatile contaminants such as VOCs, they're known to evaporate and migrate easily. That's what being volatile means. This means that these contaminants can move through gaps, cracks, and pores in soil into the atmosphere and even into homes. This is called vapor intrusion, and this is something that's raising a lot of concern. You can see it in the diagram to the left. We have groundwater that's contaminated, and then soil that's contaminated as well. And these volatile compounds can evaporate into the atmosphere and through this soil, and it can go into these different areas in homes. And that's obviously very dangerous for the people in the homes. And even if they're not going into homes, those contaminants in the atmosphere are a big risk in general. So in those conditions, we're going to have to consider a vapor collection system, and different things can affect that as well. Soil moisture, it can affect the rate of volatilization. Drier soil is known for faster evaporation, so that's something to consider as well. We can also use Henry's law constant as an indication of volatility of a substance and how it will move through the water or through the soil or air. Something we can consider as well is the chemical resistant lining system, which can be necessary for VOCs and other compounds like polycyclic aromatic hydrocarbons and chlorinated solvents. Something else to note is that removing VOCs and other harmful chemicals via excavation is dangerous because it can release vapor into the air and pose risk to workers and people in surrounding areas. So that's why containment is often used for these different type of volatile compounds, because you're not risking releasing it into the air, you're just collecting it and keeping it contained. The last physical mechanism that I'm going to be discussing is geologic and hydrogeologic conditions. There's a lot of these that we need to consider before installing any sort of containment or doing any ground modification, in order to assess what kind of containment that we want to install or what type of method of ground modification that we're going to pursue based on these different conditions and whether or not it will be successful, and a good remediation approach to take. So one of them is depth to groundwater. This is super important because you want to know how far away these contaminants are from reaching a groundwater source, a water source, and being a threat to any aquatic life or humans that are going to be consuming that water. You want to know how far away we are from that water, and that goes into soil characteristics, because these are things we need to consider, like I've already mentioned, porosity and permeability, things like that affect how fast those contaminants are moving, and that will help to determine how big this containment area needs to be, and the type of material that we want to use for the containment area, and again, the type that we're going to pursue. Then we have topography, again, has to do with what kind of containment we're going to install that will work with this environment. We also have to consider the wells that are installed within the aquifers. Like you can see in this diagram, there's different types of wells that can be installed in these aquifers, and you have to be aware of where they are, and if they'll interfere with the containment, or if installing the containment will interfere with the wells, along with confining layers and rapid recharge areas. things such as sinkholes and solution channels in these aquifers. Overall, you need to really know what's going on and what's already installed. Then we have groundwater flow direction, hydraulic conductivity, gradient, along with water table contours and possible discharge points. They're just all important factors to consider when installing a form of containment or physical barrier, and before pursuing any ground modification methods.
Containment and ground modification methods are widely used in geotechnical and environmental engineering to control or mitigate subsurface issues. These issues can include contamination, unstable soils, or generally poor soil conditions. The goal is to contain or isolate the problem to prevent it from spreading or escalating. These methods are often used as a first line of defense and are commonly followed by more direct treatment techniques. Some of those follow-up treatments might include pump and treat systems, in situ chemical oxidation, bioremediation, or thermal treatment depending on the containment type and its site conditions. Containment, as the name suggests, is all about preventing contaminants from migrating and stabilizing the affected area. The key idea is to isolate the contaminated zone so it doesn't affect the surrounding environment. Some of the most common containment approaches include slurry walls, sheet pile walls, grout curtains, and caps and liners. We'll go over each of these and explain how they're used in the field. A slurry wall is created by digging a trench and filling it with a slurry made from bentonite and water. This keeps the trench walls from collapsing during excavation. Once the trench is fully excavated, it's backfilled with a low permeability material like a soil bentonite or cement bentonite mix. This acts as a barrier to block groundwater flow and prevent contaminants from migrating. The equipment used includes trenchers for digging, backhoes for soil handling, and slurry mixers to prepare and maintain the bentonite mixture. Sheet pile walls are made of interlocking steel sheets that are driven into the ground. These create a vertical barrier to block the movement of water or contaminated soil. They are especially useful near water bodies or areas where a rigid and long-lasting barrier is needed. The typical equipment used here includes vibratory hammers and pile drivers, which help drive the sheets deep into the subsurface. Grout curtains are formed by drilling holes in a targeted zone and injecting grout into the ground. This grout then hardens and forms a barrier that reduces permeability and seals off contaminated zones. They are often used around dams, reservoirs, or underneath landfills to prevent the migration of contaminants. For this method, you'll typically see drill rigs, grout pumps, mixing plants, and packers used to isolate specific zones within the borehole. Flow and pressure monitoring systems help control the injection process. Caps and liners are physical barriers placed either on top of or beneath contaminated soil. Caps prevent upward movement or vapor release, while liners prevent downward leaching of contaminants. These are widely used in landfills and contaminated industrial sites to stop water infiltration and vapor release from the contaminated zone. Common equipment includes excavators and compactors to move and level soil, geosynthetic rollers for liner placement, and welders or seamers to seal synthetic layers. Survey tools and leak detection systems are also used to ensure a good fit and ongoing performance. In contrast to containment, ground modification focuses on physically changing the properties of the soil or rock itself. This might be done to improve stability, reduce permeability, or increase bearing capacity for future construction. Common techniques include compaction, soil stabilization, jet grouting, stone columns or vibro replacement, and deep soil mixing. Each of these serves a slightly different purpose and works best under specific site conditions. Compaction uses mechanical effort, like rollers or vibratory plates, to physically densify the soil. The goal is to reduce pore space, which increases strength and limits water flow. This is a simple but very effective method to improve bearing capacity and reduce settlement in soft soils. Typical equipment includes sheep's foot rollers for clay-rich soils, vibratory rollers for granular materials, and bulldozers or plate compactors depending on the scale of the site. With soil stabilization, chemical additives like lime, fly ash, or cement are mixed into the soil. This helps increase the soil's strength, durability, and resistance to water. It's commonly used to strengthen weak soils or prepare a contaminated site for further remediation or construction. Equipment you'd expect includes augers and rotary mixers to blend the additives, slurry injection systems and drill rigs. Soil sampling probes are also used to verify that mixing is even and effective. Jet grouting is a high-pressure technique where jets of grout are injected into the soil. The grout then mixes with the in-place soil and hardens to form columns or blocks that improve stability and reduce permeability. This is great for reinforcing soft soils or creating vertical barriers. The main equipment includes jet grout drill rigs, high-pressure grout pumps, and mixing plants. Automated control panels are often used to monitor pressure and flow in real time for precise treatment. Stone columns, also known as vibro replacement, are formed by drilling holes into the ground and filling them with gravel or crushed stone. The material is compacted in layers, which creates vertical columns that act as drains and improve load-bearing capacity. This technique is mainly used to reinforce soft, compressible ground and to improve drainage, especially in areas where rapid settlement could be an issue. Equipment for this method includes vibroflots, which are inserted into the ground to help compact the stone, as well as cranes, stone hoppers, vibratory probes, and GPS monitoring systems to control placement and depth. Deep soil mixing involves using large augers to mix the in-situ soil with binding agents like cement or lime. These binders chemically react with the soil to improve its strength and reduce permeability. This technique is especially useful for treating large volumes of weak or contaminated soil, and it's often applied where excavation isn't practical. For deep soil mixing, the main equipment includes soil mixing rigs with rotating mixing heads, grout or slurry tanks for the binder materials, injection pumps, and automated control systems that help monitor the mixing depth and binder ratios.
So containment is often chosen when fully removing contamination just isn't quite practical. This might be because the site is too dangerous to excavate, such as areas with radioactive waste, or because the cost of removal is just extremely high. In other cases, the exact source of contamination may be hard to locate or may be completely buried, making a targeted cleanup difficult. Sometimes the goal is simply to keep the contaminant buried permanently, in which case containment becomes a long-term management solution. One common example is with landfills, where engineered liners and covers are used to prevent leachate from entering the groundwater. But in all these scenarios, containment is about safely isolating pollution to protect human health and the environment. So heavy metals are often easier to contain in soil compared to other types of contaminants, and that's largely because of how they behave chemically. So first, is many heavy metals have a low solubility in water, which means they don't dissolve and spread as easily as, say, like an organic pollutant or a solvent. And second is they tend to absorb onto soil particles, especially clays and organic matter, which are negatively charged. So since most heavy metals are positively charged, they're naturally attracted to and held by the soil. So this helps prevent them from moving through the subsurface. However, metal mobility isn't fixed. It can be affected by several factors. So, for example, soil pH plays a big role because metals are more mobile in acidic conditions. And ionic strength in the soil solution can also shift how metals interact with soil particles, especially when they're competing ions. And the texture and the pore structure of the soil also matter. Fine-grained soils like clay hold on to metals better than coarse sands, and more connected pore networks make movement easier as well. Temperature can also influence chemical reaction rates, while residual time or how long the metal has been in the soil affect how strongly it's bound. And finally, amendments and additives like lime or phosphates can be used to reduce mobility, but their effectiveness depends on site-specific chemistry. So even though heavy metals can often be effectively contained, a lot depends on the soil conditions and environmental context. Another major factor to consider is how close the contamination is to groundwater. If the water table is shallow, then there's a greater risk that contaminants will move quickly and reach drinking water sources. This means that any barrier must go deep enough to block those flow paths. So in some cases, the pressure for moving groundwater or the hydraulic gradient can push pollution under or around barriers, especially if they weren't properly built. Also, the water table itself can rise or fall with the seasons, and if it rises into a barrier that wasn't designed for saturation, it can break down or leak. So, groundwater proximity has a big impact on both the design and long-term success of a containment system. Not all containment materials work for every containment. So, some materials, such as certain clays, can swell or shrink depending on what chemicals they come into contact with, which could lead to cracks and leaks. Stabilization and solidification methods also depend on chemical compatibility. So, for example, what works well to trap heavy metals might not be effective for trapping hydrocarbons or organic solvents. Using the wrong combination can actually speed up contaminant movement instead of stopping it. So this is why matching the barrier or treatment material to the specific contaminants present is a critical part of the site design. Vegetation can also play a role in containment. So phytostabilization uses certain plants to reduce the movement of contaminants, especially near the surface. The root systems help prevent erosion and runoff, which could otherwise carry pollutants into nearby water bodies. Some plants can even bind contaminants into their root zones, keeping them from moving deeper into the soil. Also, vegetation helps keep barrier covers intact by protecting them from weather and helping with water regulation. So even though plants might seem passive, they can be a valuable part of a multi-layer containment system. So now I'm going to go over some case studies where containment and ground modification have been used to highlight some of their successes and some of their failures as well. So first up is the Hanford nuclear site in Washington. So this site produced plutonium for nuclear weapons and left behind large volumes of radioactive waste. So to stop this waste from migrating into the Columbia River, slurry walls were installed around key areas. So these walls were made by mixing clay and cement to create a dense, low permeability barrier. And the idea was to physically block groundwater flow and trap radionuclides. And it worked fairly well. Migration was slowed and containment was achieved, but it wasn't perfect. Over time, some small fractures or material weaknesses allowed for some leakage. And so this case reminds us that even effective barriers need backup plans, monitoring, and sometimes reinforcement as well. So an important lesson from the Hanford nuclear site is the role of site-specific geology. So the success of the slurry walls depended heavily on uniform soil conditions. In areas with more fractured rock or uneven layering, contaminants had more pathways to escape. So this highlights why detailed site characterization is essential before installing a barrier. It also shows why long-term observation wells are often placed around the perimeters to catch problems early on. So Love Canal is a textbook example of environmental mismanagement. So basically, industrial chemicals were dumped in a site that was later developed into a neighborhood, and people got sick and the community demanded action. Eventually, the site was capped with a thick clay layer to stop rain from soaking through and creating leachate. And underground walls were added to contain what was already in the ground. And these efforts did significantly reduce the spread of contamination and it made the site safer. But the initial failure to act quickly meant that major contamination had unfortunately already occurred. And even now, regular inspections are required to ensure that the barriers are still doing their job. This case also illustrates the importance of a public pressure and policy change. Um, Love Canal became a national symbol for environmental reform. It helped lead to the creation of the Superfund program in the United States. And it also raised awareness that technical fixes like caps and barriers must be paired with a good communication with the community to rebuild trust in affected areas. So next up is the Bhopal gas disaster site in India. So after the 1984 gas leak at the Union Carbide plant in Bhopal, much of the attention was on the air pollution and immediate deaths, but the site itself still remained contaminated with heavy metals and pesticide residues. So to address this, remediation teams turned to soil stabilization. They used lime and cement to chemically bond with the metals and reduce their ability to dissolve and move. And this worked well in the zones that were treated thoroughly and was far less disruptive than digging everything up. But it wasn't a complete fix. Some areas were missed, and groundwater contamination still persists. It's a reminder that consistency and full coverage are essential. What makes Bhopal unique is the long timeline of inaction and a lack of cleanup. Even decades later, debates continue over the adequacy of the response, and this highlights the need not only for scientific solutions, but also a strong regulatory follow-up and international cooperation, especially when contamination spans across generations. So a really wide-known disaster was the Fukushima nuclear disaster. So following the nuclear accident, a big problem was that clean groundwater was flowing into the damaged buildings, then becoming radioactive and then leaking back out. So the solution was that engineers built a frozen soil wall around the reactors, and using pipes filled with liquid nitrogen, they froze the ground solid, creating a kind of ice shield underground. This reduced water flow into the buildings and cut off one source of radioactive waste. And it was a clever, minimally invasive solution, but keeping the wall frozen takes a lot of electricity, and if the system fails, the ground will thaw and the barrier will then disappear. So it's an example of a high-tech solution that works well, but needs constant support. So Fukushima also teaches us about the importance of rapid response and innovation under crisis conditions. The frozen wall was not part of the original design. It was developed after conventional methods proved too slow or ineffective, and it shows how engineering must sometimes adapt in real time to extreme solutions, balancing practicality, cost, and urgency.
To understand the applications and limitations of the possible methods of containment and ground modification, we must understand the definitions of these. Containment can be defined as the attempt to prevent the spread of contaminants and stabilizing a problem area to prevent damage to surrounding areas. This includes slurry walls, sheet pile walls, grout curtains, and caps and liners. Ground modification can be defined as the improvement of the physical properties of soil or rock in order to increase stability and suitability for construction. This includes compaction, soil stabilization, jet grouting, stone columns and vibro replacement, and deep soil mixing. As previously mentioned, a slurry wall is a trench that is dug and filled with a slurry, typically bentonite and water, in order to prevent it from collapsing. One of the many applications of slurry walls are the ability to block groundwater flow or contaminant migration. Another application would be to provide subsurface containment for a wide variety of waste, including radionuclides, metals, and organics. Another application is the thickness of the slurry wall and the method of trench construction can ensure wall integrity. Some of the limitations of slurry walls are that it requires bentonite and water. Sometimes the soil bentonite mixture cannot withstand contact with chemicals such as strong acids, bases, salt solutions, and certain organic chemicals. And physical factors such as seismic activity and pressure buildup can degrade or deteriorate soil walls over time, causing them to lose their containment capacity. Another method of containment are sheet pile walls, which are interlocking steel sheets that have been driven into the ground in order to form a barrier. Some applications of sheet pile walls are that they are used to block water or soil movement, especially near bodies of water. They are lightweight. They have the ability to be reused across various construction sites, have high resistance to pressures and stresses, and have a fairly long service life. Some limitations of sheet pile walls are that they are usually not suitable as permanent solutions, have difficult installation based on soil types, and installation can disturb surrounding areas through vibrations and noises. Grout curtains, which are another method of containment, are when holes are drilled and injected with grout to form a barrier underground. Some applications of grout curtains are that they are used to reduce permeability or seal off contaminated zones, they can be used up gradient of the contaminated areas to prevent clean water from migrating through waste, or down gradient to limit migration of contaminants. They can also be used at shallow depths, a maximum of 30 to 40 feet. They are also cost effective. Some limitations of grout curtains are that they require an underground injection permit, that maintenance includes keeping the nozzles clear, maintaining airflow, and effectively creating a wall without defects. For example, if very coarse grained materials are discovered, it may result in damages to the curtain. Thus, the site must be well examined to characterize all obstructions and geologic conditions. Furthermore, their turning off and on of the jets may cause them to be clogged. Additionally, the jet orientation is crucial in making sure that the current is continuous. It can even be possible for magnetic anomalies to create problems within the orientation of the directional tool. Another method of containment are caps and liners, which are implemented by placing caps on top or liners beneath the contaminated soil in order to isolate it. They are also often considered geomembranes. Some applications of caps and liners are that they are used in landfills or contaminated sites to stop water infiltration or vapor release. There are also many available options for installation based on the site conditions. Some limitations of caps and liners are construction quality issues, which are viewed as the principal limitations of the performance of geomembranes, such as caps and liners. Another limitation is to avoid the co-disposal of liquid waste without fully assessing the potential impact on stability. Furthermore, another limitation is hydraulic issues, physical and mechanical issues, and containment transport issues. Now we will discuss the applications and limitations of ground modification methods. The first method discussed in this presentation is compaction, which is when mechanical efforts such as rollers and vibratory plates are used to densify soil. Some applications of compaction include the increasing bearing capacity and the reduction of settlement, as well as tightly packed soils that allow for less water to flow through. The limitations of compaction include the possibility to be marginally effective in treating silts, and this is specifically in compaction grouting, as well as that it could be applied beneath lifelines but may not sufficiently compact soils immediately adjacent to the lifelines, and once again this is specifically in compaction grouting. Furthermore, another limitation of compaction is that it requires mechanical effort such as rollers and or vibratory plates. Another method of ground modification is soil stabilization, which is the addition of chemicals such as lime, cement, or fly ash that is mixed in with the soil to strengthen it. Some applications of soil stabilization are that fiber-reinforced soil has often been characterized as a single homogenized material, as well as that it improves strength, durability, and resistance to water. Some limitations for soil stabilization is the need for laboratory characterization, which has been a major drawback in the implementation of fiber reinforcement in soil stabilization projects. Additionally, another limitation in soil stabilization is the requirement of the addition of chemicals such as lime, cement, or fly ash. Jet grouting, another method of ground modification, is when high-pressure jets of grout are injected into the ground to mix with and strengthen the soil in place. Some applications of jet grouting include that it can treat all liquefiable soil types, that when it is well cared for, it can improve soil conditions immediately adjacent to lifelines, that it improves mechanical and hydraulic properties, as well as it performs well in creating underground columns and improves soft soils. Some limitations of jet grouting are that it requires high levels of maintenance and requires high pressures. The next method of ground modification discussed are stone columns and vibro replacement, which are when holes are drilled and filled with gravel or crushed stone, compacted to form vertical drains and support. Some applications of this are used to reinforce soft ground and speed up drainage, that it is less expensive and can be used within 1 meter of many lifelines. Some limitations include that it requires gravel and stone and also requires pre-augured holes. Finally, the last method of ground modification is deep soil mixing, which is the use of large augers to mix soil with binders such as cement or lime in situ. Some applications of deep soil mixing are that it can be used to treat large volumes of weak or contaminated soils, that it can treat all liquefiable soil types, specifically in situ soil mixing, and that it could possibly be effective when employed a short distance away, roughly 1 to 3 meters. Some limitations of deep soil mixing are that it requires large augers to mix soil with binders in situ, as well as that it requires the addition of cement or lime.
When it comes to containment methods, costs can vary widely depending on the site conditions, materials, and installation complexity. Starting with slurry walls, the material cost is around $86 per cubic yard, and installation can cost an additional $28 per cubic yard. For sheet pile walls, carbon steel sheet piles range from $30 to $60 per linear foot, while galvanized or corrosion-resistant options can be between $60 and $120 per foot. Installation adds another $40 to $100 per linear foot. Grout curtains, also known as grouted cutoffs, cost roughly $25 to $40 per square foot. And finally, for caps and liners, a clay cap or geosynthetic liner will both run about $9 per square yard, and full installation of a cap can range anywhere from $80,000 to $500,000 per acre, depending on the site size and complexity. Now, looking at ground modification costs. Again, these numbers are all estimates and can vary by project. Compaction techniques include deep dynamic compaction, which costs around $5 per cubic meter, and vibro compaction, which is slightly cheaper at $1 to $4 per cubic meter. For soil stabilization, admixture stabilization using lime or cement is typically $2 to $4 per cubic meter. If you're building structural support like mechanically stabilized earth walls, that can be around $225 per square meter of wall fence. Reinforced slope stabilization comes in at about $45 per cubic meter, and soil nailing can cost anywhere from $165 to $775 per square meter face, depending on depth and length. Lastly, jet grouting is one of the more expensive options, running from $200 to $650 per cubic meter. Here are 2 more advanced ground modification methods with their estimated costs. Stone columns or vibro replacement typically cost about $45 to $60 per meter, or about $30 per foot. Full installation of these columns on a large site may total around $430,000. Deep soil mixing is a bit more complex and expensive. The soil mixing process ranges from $100 to $140 per cubic meter, and if you're installing columns, that might cost about $50 per foot. A full column installation can run close to $525,000 for a typical site. Keep in mind that these costs are highly dependent on factors like site accessibility, soil conditions, contaminant type, and whether specialized equipment is needed. Here we have a quick visual summary of how the costs of different containment and ground modification methods compare to one another. On the left side, we have a vertical scale ranging from low at the bottom to very high at the top. Each method has been placed along this gradient based on average implementation costs. For containment methods, caps and liners tend to be the most affordable. They fall in the low to moderate cost range. Grout curtains and sheet pile walls are generally a step up, falling in the moderate range. Slurry walls are considered moderate to high, depending on the depth and material used. On the ground modification side, compaction is the most cost-effective and falls into the low category. Stone columns or vibro replacement and soil stabilization fall around the moderate to high range. And finally, jet grouting and deep soil mixing are the most expensive, landing in the high to very high category due to the specialized equipment and complexity involved. This breakdown helps decision makers choose the most appropriate method, not only based on technical performance, but also on budget.